Good morning, everybody. My name's Simon Bradwell from ebm-papst here in Melbourne, and today I want to talk about power factor correction. Power factor correction. First of all, why do we have to correct for power factor? Most of you know that efficiency of pumping systems are controlled by fan laws, and if we reduce the speed of a product by 20%, we typically get 50% power savings. This means that in fan systems, more and more electronics is being used, either on board or off board. So a typical PCB like this, for instance, could be found in majority of air movement systems. However, what's happening inside these products? Well, a lot of electronic products have capacitive or inductive type properties. And we define, when we have a sinusoidal voltage supply, something called power factor. And what happens when we have a lot of electronics like this is that the capacitor type products get charged with electricity. Inductive type products induce magnetic fields inside products. And this causes the voltage and the sinusoidal characteristics to shift, like you can see in this diagram here. Now, what does this mean? Well, this means that we're putting power inside the electronic components that isn't useful. What we really want to do is to drive the fan and drive the rotation of the fan such that we're putting as much electrical energy into air energy and air power energy as we possibly can. So we define something from this called reactive power. So in this diagram, typically we're here in Melbourne, so we're using coffee as an image. We can look at total power, we can look at reactive power, and we can look at real power. Now, what we want to do is to get as much real power as we possibly can into the air movement. So what we have to do is to correct for the capacitive and inductive type characteristics inside the electronics using further electronics. Now, inside our EC plug fans, the large ones, 1.5 kilowatt and above, we typically have active power factor correction on each of the three phases. Now, there is non-active and passive power factor correction available in several products as well, but the best you can get is active, because as the load changes, then the characteristics of the electrical supply also changes, and therefore to have an active response is a really good thing. So what happens and why? What's the effects of this power factor correction? The main features of a three-phase EC plug fan are shown here in this diagram. So effectively what we're doing is correcting the power systems and making it smoother inside the system. So in a lot of buildings, for instance, in hospitals or data centers, there's a power system inside the building. So a combined heat and power system, for instance. And these combined heat and power systems, they need a good, smooth electrical supply inside the building, such that the harmonics are low. So typically they'd ask for a total harmonic distortion on the voltage line of less than 5%. And by using active power factor correction systems, you can get the harmonic distortion low. Now, it's really good to get this correction done at the source inside the motor, for instance, because that makes the whole system plug and play, and away she goes. It's very easy. In data centers, for instance, the enablement of having active power factor correction inside the systems means that you can reduce the transformers required, like in this diagram, or the power generation systems required, such that you can save money. So hopefully that's been straightforward. Today I've been talking about power factor correction. I've talked about sinusoidal systems. I've talked about total power, reactive power, and real power, and how good that is. I've talked about what happens inside an EC plug fan and the aspects of active power factor correction. And I've also talked about some of the benefits that you can get from active power factor correction. So I hope that's been useful. If you've got any questions, please contact us in the normal way. Thanks for watching.